doing a little bit of late night stream, at least for me. And let's see, I've been working a little bit with actually like an IR for Runic because I thought it would help with like making like a debugger and some of the features of the language might be easier, question mark, or and I've never done like an IR before. Well, I've made like a compiler straight to assembler assembler basically, but never like an intermediate language. So it's interesting. Hello Blue, can you handle the error using the switch case? Which error? Were you talking about anything in here? Yo Penguin, what's up? Or I'm just gonna, let's see. Did we leave this in a reasonable state? Yeah, that's good. Can you handle errors using switch case? I don't know actually. I usually either do like catch or, well, okay, so I'm assuming you mean essentially if you have an error let's say we have error function this returns an error, right? And then so usually, okay, let's say we have an error type that has like error 1, error 2, and you can be any of those. And then over here we would say, well, let's say we actually have some kind of type we want here. So let's say n is equal to error function. And then here, if you wanna, so one thing you can do is, well, there's even a thing here. So you can catch the error, capture it, and then switch on it directly. So this part will be a switch expression here. So that means that whatever's the result is of this switch will be put into n unless you like return or anything. So this is how you could do it. And here you have like error 1. If it's this error, we do something there. If it's error 2, we do something with that. I don't know if this shouldn't really matter here, but we can say something like this. Usually you would probably like log error 1 happened, you know. And if you want to log as well as, so let's say let's say we want to log but then also return some kind of fallback. You can add a break label here and then break that, and you can also do that there as well. Now let's say we add another error, fatal error, and if we get a fatal, we will, yeah, you can simply return the error to just make the main get the error instead. We can also have like a fallback. So if there's a fallback, we can just say, I don't know, 3, and that's the fallback for that error. So are you talking about this, or what are you talking about? Because now, if let's say we do like error 1, and then we run this, we would get undeclared standard. Okay, there we go. Oh, it's unused. Okay, let's do like n equals this. Yeah. So here we got error 1 happened, n equals 1. Is it that what you mean, or what do you mean by handle the error using the switch case? Because I was thinking first that you meant like, let's say you just call like this, but you don't handle the error here. You do like a switch on X, but I'm not sure if you can do like a switch on X directly. Like usually you would catch it like this and do something in case of an error here, or just bubble it up with try. So yeah, but this is how you would have different kinds of errors, and how you can, you know, catch and handle the error here. Hello, the coding youngster, welcome. All right. I'm just gonna push this for now. Because I wanna go back. I wanna show a little bit on the IR stuff that I've done. Let's see, and or. How's the language going? Can you show some examples? Yeah. 1 second. I'm just going to actually, let's switch to the IR branch. And I want to God damn it. Wait, merge. What's happening? Alright, I don't know what happened there. I think I had like an outdated IR. I don't think I have, maybe I did work on this one. Anyway, yeah, so I'm gonna show you, so I can go to the MVP here. So basically I have like MVP SH on, so basically kind of like a test suite showing all the things that exist right now. So on the right hand side is the bash version, and on the left hand side is runic. So here you can see basic like calling commands with arguments, and here's a basic pipe thing. also check that every output is exactly the same as bash, which it is, but there are some differences when it comes to like echo, for example, because this echo is the executable echo, while this echo is the kind of built-in shell thing. But there's some differences with like the new lines and storing it in a variable, which, but anyway, so here's like an if, just standard if here. Now the syntax is kind of, it's gonna be like a mix between bash and zig. So this syntax here, I mean this if is very basic here, but the idea is that we would have zig syntax here. So here you can see like the first is a thing of that, which is like a for loop here with a range from 0 to 10, well, exclusive, and the capture here of I, and we can loop through that. And here here's how we have can you make them like, I know you can do like diff this to keep the scroll the same, but I'm not sure, but that will show like a bunch of differences though. Anyway, so here's like n equals 4 here, and then there's like, you have to do like some kind of, so this is basically if you want to have a variable that governs what the range is, you can do that. And in bash, I'm not a bash guru, so I had to like Google some of these things. So in here it's basically you call this sequence thing, which will make a sequence, which is kind of cool. I mean, it's kind of cool that you can use utilities like this to make kind of like like an array. And I would probably try to think of how to maybe do this in this language, although for this example it's like it's not really needed, it's like built into the language. So but anyway, yeah, and then the rest is the same. Here we got like functions. So basically functions are supposed to be like, well, functions are not really done yet, although you can define a function and you can have parameters, you can pass parameters in, you can call a function, it will do whatever's inside with the parameters. It also has closures, so you can have like it can reference things from outside of its own scope. But piping does not work with functions yet. The idea is that you would have piping, and you would basically, a function would be like a mini, or well, it would be like an executable basically that you define. But right now they don't, like, we don't support like piping functions yet, or piping anything like that has like a block or anything. It's just executables right now. I don't remember if we allow like strings to be piped, but the idea is that we would be able to allow a lot of things to be piped, but right now it's just executables you could think about. But yeah, you can define functions and do some calls in here, do whatever, and call it as well. Bindings is just, binding things to names. So this is a constant called string x, and this is the value of that. And now what's important here as well is that this actually now binds the type of string to the thing, and we have like statically typed, strongly typed variables, so, or yeah, strongly typed things. So basically you can't then change the type of this. It's gonna have string as a type, and if you wanna make a number or something out of whatever's in here, you would have to make a new variable, or call a function or something on it to get a number. or set it, like you can't set this to something that's not a string. Actually, you can't set it at all because it's a const. So, but and then I found like well, and the equivalent of like, well, if you want to be able to set something like you have it mutable, you have to use var. Just like in zig, it's const and var. So const is constant, var is variable. And in bash, for a constant, you would use declare -r, and then the name, and then equals, and then the thing. I didn't actually know you could do that, but that's how that is. And yeah, and then you can use string interpolation to get the thing in here. So this would be hey Discordianism, you know, printf with string x in here. And then we also show that this is like an execution result. If you bind it to a name like this, it will become an execution result, which means that you can extract, for example, standard out from it to get the result of that. Okay, and here we have like integers, basic like integer, you know, arithmetic. So also another note with interpolations, we don't have several different types of interpolations. The only interpolation that exists is this one, and it's just, you know, the thing inside is going to be the you know, a runic expression basically. So yeah, that's it. And you know, we support arithmetic expressions directly like this. You don't have to wrap it in double parentheses. All right, see you later, Discordianism. Thanks for stopping by. Yeah, so that's it there. Floats. I didn't actually know that Bash did not support floats like natively or whatever. But you could use floats, but it's you have to use something like BC, which is fine. I mean, as long as you know about it. But I mean, in my language, then in Runic, you would be able to just use it directly. And then we have compound assignment, which is a new word that I learned recently, which is these like plus equals, minus equals, and that does exist in Bash as well. Although you have to use these arithmetic like you know, wrappers here, but it does work. And but it only works for integers, so that's what you have to keep in mind there. I guess if you wanted to use floats, you would have to use like BC somehow to do this. Maybe there's like probably a good way to do it, but anyway, this is how it works in here. Also, there's no requirement when like assigning variables that you have to have like no spaces in between or anything like that. You can have as many spaces as you want between these, and that's that. The only thing you can't have, I think, is like a new line like this. It has to be on the same line. Okay, so then we have booleans, and here is like an AND table, which just shows, you know, the basic AND table, true, false. We show that how you produce these values, you use the keyword AND. Although I think now we can also do this. This is basically gonna be the same thing here. And I'm leaning towards actually doing this instead. Even if zig does allow you to say, or as zig actually has AND or, however, I think that Runic should probably adapt the Bash way of and or because of the fact that it's so commonly used with the pipelines. And so we would like to have the pipelines basically very close to how Bash does it. And for like booleans, which is basically gonna be a test of exit codes, or like exit status or whatever, then it's gonna be, you know, this double ampersand, but whatever. We might actually enable both if you want. But okay, And anyway, I should say I, but okay. So yeah, so that shows that. And here's a kind of a cool thing that I also figured out. So basically, if you have a block, you can echo a bunch of things in the block. If you bind it to a variable, now everything that was echoed in here is stored in the variable. It's not echoed out to the to standard out. It's like stored in this one, and then you can use it here. You can echo it or pipe it directly if we like start to enable that. But for now, you could use like echo and table, and then pass it into column to make a table like neatly you know, formatted and all that. All right, so here we have the OR table. Also, yeah, I should show the way I did it over here, which is a little bit, okay, this bool to string, we don't actually need this here. I'll remove that. So here basically we have like the AND table. I'm using like this thing here, which is like, yeah, it's set to this expression here, which is cat with a here doc, and this is just a string here. So, and then but we do interpolate here, so this is like true and true, and then we echo this, because otherwise this won't really like echo out anything. It would just be, I think, the like status code of what you put in here. So this expression will like just return kind of like an exit status. It won't like output any echoing to the standard out or anything. But if you echo the exit status here, or exit code, it will actually, you know, this expression will kind of show what the result of this was. And that's just because, like, yeah, in Bash, the booleans are basically exits codes as I've understood it. So yeah, so that's how we do it here. And here is kind of like, okay, well, we can show, or we can make the exit codes like this, but then we can also coerce it into a string by using it in a string interpolation, and it will actually show why, or whether it's like, well, what kind of exit code it is, or exit status. So this would result in 0 because of, you know, how Bash, how like the processes work. If they return 0, it's a success, you know, it's true or whatever, and everything else is 1 here. All right, so, and the same for OR. Here we got arrays, so we have a basic array here, 1 to 3, and then you can also loop through arrays with just putting array in the for, and you can capture the item out and echo it like this. And here we're showcasing like a for expression here as well, or an inline for, whatever you want to call it here. And here's a for loop with 2 things in the like sources, as I call it here. So we have 2 things in the sources. It's basically going to be this array, and then this range, which is open-ended at the end. It doesn't have an end, so it will match the end of whatever like other thing in the sources is here. So it will have the same end as the length of this array, which means that basically we're looping through an array, but then we also get the index here. So here we're capturing item and I to get the index and item here. Okay, so that's basically what we have right now. There are a little more small things as well that I'm working on as well, but so that's the status right now, and the plan is to I really want to make functions work better to be able to like pipe functions, but that's such a, it feels like a huge undertaking. And right now I'm kind of rewriting the compiler, or not the compiler, but the evaluator and the well, basically the evaluator. I'm adding a step of like intermediate representation. So I'm making this IR language, which was what I was going to show here initially. So if we go to IR, let's go here. Well, first, actually, I'm gonna show this. So if you have this flag enabled, enable IR, we run the IR instead of running the normal evaluator. So now we're running this IR, and what it's doing is basically we accept the AST as normal, but instead of running it through directly and executing everything directly, we first compile it into this IR language and then evaluate the result of that. So we basically have two steps now before actually running or evaluating the code. So first we compile and we get this context out, and then we show some debugging information about whatever we have, and then we run the context. But what's nice about this as well is that you can run the context, but also when doing that we create this evaluator, and what's happening in here is that every instruction that we run is manually stepped through like this. And basically what that means is that you could potentially like build some kind of debugger here, which you would like, yeah, I want to step through the next thing, I want to step through the next thing, and yeah, that would enable a lot of things actually. But one of the cool things would be to have like a debugger. Another thing would be to have virtual threads, so that we could run pipelines basically like in the background, and also through this system only, so that we don't have to create like real threads, so to speak. We could create virtual threads that runs things in the background, because here, like when we evaluate the next step, we could choose like, okay, well, we could have several things we could step through, and if we have 6 threads or whatever, we could step through each thread and handle it like that. So here we kind of, instead before where we had to like, we pass the AST to the evaluator and it would run through everything at once. But here we can actually, since we've divided the AST now into a list of instructions, we just step through the instructions and we can stop whenever we want, we can resume whenever we want, and yeah, so that's kind of cool. And let's see, let's show well, we have the compiler here that compiles the thing, and we get this context out. So basically the context has like a read-only part, which is the instructions and read-only data. Actually, let's just show what the result is, because I have this I'm gonna source session vim, and I'm gonna go to IR. So here's like the IR example right now. It's very, very simple, and I also added this return statement so that we can like test the exit code as well. But basically I press F5. Oh yeah, I need to change this a little bit here. No, let's do that. All right. Unknown option, enable IR. What? Oh, did I get? I need to build first. And we got some errors, so let's check that out. Oh, I left it in a kind of an error state here, but okay. I can't really show that right now, but basically, okay, let's see if we can. Okay, I'm just gonna do this for now. I was trying to add if expressions here. Ah, shoot. Where is that coming from? This one maybe. Yeah. No? Oh, this one perhaps. Wait, location. What's happening? Location slice exit code. Oh, adder maybe. I have this like format function. Oh, we do have format there. So let's add this over there. Was that the issue? Thank you, piano. Oh, wait. Oh, yeah. There we go. Okay, there we go. Now it should be built. Okay, now let's check this out. So we have this very simple thing here. If I run it, first we see the compilation results. And first we have like the read-only data here. And we have some strings in here, which is hello and echo. So basically that corresponds to this constant string, which is placed in this read-only data section, and then the echo as well, because this is used for calling the command. So it's placed in the read-only section here, so that we can call this command using echo and hello. Those are actually the arguments to the call function. So, and here are the instructions of the whole program right now. So basically, the only thing that's happening is the echo and then the return. This doesn't actually compile to anything right now because it's not used anywhere, I guess. Yeah, so it kind of solved itself almost, but it should probably be compiled to something, because we need to kind of keep this as like a reference. So we're probably this is going to be compiled to something. But anyway, this is compiled to this part, and I do also keep track of which expression is the source. So potentially, like when we're doing like a debugger or something, we like checking the output, we could also see that, okay, well, echo hello is the result, well, or this part is the result of echo hello. Also, we have like double exit 0 because we automatically add like an exit 0 at the end anyway. We don't really need to because we're kind of controlling the thing, but it's the usual thing you have at the end of the program. Like in a real like assembly program, you would need to have some kind of exit at the end. Otherwise, the process, like, it wouldn't know where to exit. There's not like an end. I mean, I guess technically, okay, whatever. Anyway, so we push, and this is a slice. So we're pushing this value. So basically how it works is the push can push any kind of value, and the values right now are kind of basic things, like literal values. It can also be a location, and this is kind of like a location combined with a length, which is a slice, right? It's a pointer basically, and this is the address here. So this is the address, which means the kind of, well, this symbol here, the hashtag or whatever it's called, the number symbol, it represents like an absolute kind of address into the read-only data here. So it's because it's read-only, that's what this symbol means. And the first is the page number, which is page 0. The second is the actual address in the page, so 0 is over here. And then we have the length, which is 5, so you know it's hello here. And then we have the next slice that we push. So basically what we're pushing here are the arguments to the call. And then we're pushing how many arguments do we have? Well, we have 1, except we have 2, but I'm kind of counting the first one automatically, so it's gonna be 1 plus 1. And then we initiate the call thing, which is kind of magical. Well, it's not really magical, but it's more, you don't really see what it's doing here. But basically what it's doing is first it's popping this to see how many arguments do we have. Okay, then it loops through and pops every argument, builds it into a list, and then it calls the actual the echo hello here. Okay, and then we have the exit 0. And then we can see when we run here as well, we can see everything that's happening here. So here I'm putting out the instruction counter, which shows which instruction we're on, like 0 out of 6 here. Okay, well, I guess it's 0 out of 5. This is like the length, whatever. And then we're executing, we're seeing which one we're executing. It's stepping through, we're executing this. We're stepping through here, it's pushing this. And then we're on the call, and you can see we call hello here, or there we go. and then we get to this part, which exit out. So there we go. All right. So now if we change this to 1, for example, we can run this, and you see Vim here reports that it returned 1 as well. So you know it works. If I change this to 3, it will report it returned 3. Okay, but then you don't actually have to have that there. It's just that it was just a test there. We do add this automatically over here. Hello, Commander Thrashton, welcome. Not another bash like. Another one. That's kind of interesting, because when I started this project, I kind of wanted to go in blind without knowing any other. I mean, I was sure that would probably exist a bunch of them, but I didn't want to go in and look at what existed out there. I wanted to go in with 0 influence and just make my own version here, which is kind of saying like my own version, but it's more like, you know, I'm taking syntax of another language, mixing it with bash, and that's the result basically. There is a bunch, more than you think. All right. But I'm not going to be deterred. More than you even think now after that. Okay. I mean, I know there's like a whole bunch of shells out there. Like there's a whole bunch of these other types of shells, but you know, I've never really dug into any kind of any of those. You made your own language as well, but it was not bash-like. Okay. All right, cool. What kind of language did you make? Oh, it's considered a sin. Okay. Why is it a sin? Is it because bash is holy, or what? A Lisp-like. Okay. I see. Interesting. Why? I mean, that would be considered. How many Lisp-likes are there? The point was to learn how to do interpreter and then how to do compiler, right? Because bash is the opposite of holy. It's unholy. Well, that's why I'm trying to make it better. Because I really think that it has its use, and I don't want to have to battle with the syntax of bash, and that's why I'm trying to make my own version so that I don't have to do that. Lisp is easy to parse, and I was not interested in parsers. Okay, fair enough. So do you like parentheses? I like pipes right now. Nah, I'm just joking with wasn't even into common lisp like 6 years, so I don't mind them. I was really into common lisp. Okay. Yeah. I see. I think it's probably something that you get used to. I've never done any Lisp, although I've seen a lot of it, but I mean, I've done like Haskell, but yeah. I don't know. It's just that when you look at it and you're not used to it, it's just a bunch of noise. But yeah. The same could be said for some of the symbols in other languages as well, but yeah. I even tried to make the if statement have no parentheses, which worked until I also made blocks, like curly brackets, like optional, and then it didn't work that well. So I just, okay, whatever, let's just add parentheses to the condition of the if, and that's it. But yeah, it was a very zig-like anyway. Okay, so right now this is basically what we have right now, and I'm trying to add if statements, and I'm getting all these basic like IOR issues that I'm trying to figure out. So whoops, I just killed that in the wrong way. Wait, did it disappear on its own? Okay, whatever. All right. So let's see. Okay, so yeah. So we have the compiler, and I was making this if statement here, which was very interesting because it was kind of like, well, the issue is it required a bunch of new things. So I added this new thing here, which was like refs, which is kind of like a place to store variables and also a way to speak about the same. It's just kind of like a variable declaration, really. It's a variable declaration, but it's like it doesn't have any type or anything. So it's basically just, hey, I want to have somewhere I can store the result of this if, because the if is supposed to be an expression that you can get an actual like value out of, so that it can be used, for example, as a ternary, let's say. Okay, so that's one thing that I needed to add here. And then we have the condition, which we compile here. And then what you get out is basically a value that you can use, which could either be a location to where the result is stored, or the value itself, if it's like, you know, a literal value. What else can it be? I think that's it, basically. Or you can also get like a ref, I guess, now. But yeah, so that's the condition there. And then we have like, I had to add these things like the labels. So basically we can have labels, and we create a label with like a name, and we get a key out so we can talk about the label, but we don't know what the address is yet. So, but we need a way to talk about this position here. So we have to kind of create a placeholder for an address with a label here, so that we can then, actually this is else, so that we can then say that, hey, we want to jump to the else, but we don't know the address yet. So then we set the address somewhere over here. Here, set label. Here's the else address. Set it to the absolute value, the absolute address over here. Because as we're going along here, we're actually adding instructions to the instruction set. So So yeah, I've never done this before. This is how I'm doing it right now. I'm currently in the process of like experimenting and trying to figure out how to actually do this. I've done a little bit of assembler, but I'm not like an expert at any, by any means. So I'm just trying to. I'm following like along of what I know myself, and yeah, I'm just trying to solve this puzzle here, which is a fun process. So. Yeah, so the after address is like the address of where you would jump when we're done. So that's setting done here when everything is done. The else is like if the condition was false, we jump to the else address. So that's what's happening here. And here's the then part, which we have to compile and put here. But then is the question, okay, what we do with the then? Because that's what we are trying to say. So basically here is that I add this instruction here, which is basically saying, hey, when we get this result back from the then expression, we want to add a set instruction that sets the result here to the value of then. And then we jump to the end here. We jump to the after. Well, I'm trying to make it, well, okay. This is like the beginning of the sort of, it's compiled to an intermediate representation that I designed, or I'm currently designing as I go here. So before, well, the thing that I have right now is, so this is new. This is the new part. Before, I just took the AST that we got from the parser and just interpreted that straight away. Because there's a couple of reasons. It was getting like quite cumbersome to think about the pipelines. I mean, there's probably a way to kind of solve it, but there's a couple of reasons. So basically, background processes and streaming through the pipelines to make, like, you know, one process put things into the next process and so on, you know, through the whole pipeline. It doesn't have to be a process, by the way. It could be a function that takes standard in. It could be something else that also does that. Like, it could be any, like some kind of language construct, you know. And in order to do that with the current kind of setup where you just hand a function the AST and it would like churn through the entire AST at once and then be done, basically. So that the whole setup there was, I could have modified it a bit to kind of make it work, I guess. But I just feel like, okay, well, why not just make this IR and try to, well, at least try and experiment with it, because what it could solve is basically, well, for one, we would get like a debugger almost, like for free almost, because you can step through each instruction step by step. You don't have to kind of do everything in this whole in like a one go. You can step through each instruction step by step and control it manually. So the next thing it would allow is having like virtual threads, so that you can actually spin up these pipelines, keep them in, like, add a virtual thread for each process, each pipe, which would, like, you know, forward whatever output from the previous like executable or function or whatever into the next one through the pipe. And we will be able to do that with these like virtual threads that we can now easily create using an IR like this. I say easily, but in theory, it would be possible anyway. But yeah, then we would need to have, you know, a thread, whatever. It needs like its own context. It needs, you know, its own like registers and all that stuff. But at least it's, you know, I can see how it's possible, and how if we design the IR with this in mind from the start, we will probably be able to do the things that I want as well, and get, you know, closer to a compiled language as well in the meantime. And that would be kind of cool if we can actually make this first into the IR, which is very close to assembler, and then or assembly, and then you know, if you want to take the step, you can as well. But it's not really, there's no point in doing that. Well, there might be actually. I mean, yeah, we could compile it fully and then just execute it, or we could just interpret the IR. That's what I'm going for. So first I'm gonna interpret the IR, which is also very easy. Like the interpretation of IR is just very straightforward. It's the compilation. The compilation is the compilation, and the design of the IR is what's hard here. Because that is what's kind of setting up everything to be possible to do. And it's fun as well. So, and I have made not really an IR, but more like a almost like compiling straight to assembly. Well, yeah, basically it was compiling straight to assembly, but it's my own version of assembly, another language that I did, which well, it was not a complete language, but it was basically the starting of the language, and I compiled straight to assembly and then straight to machine code from kind of this assembly code. And the assembly code I made myself, and also the translation from assembly to machine code, everything I did myself, and also creating the executable as well. But, you know, then I learned, because I wanted to learn how it was done. But now, you know, I would probably use some kind of tool to do it, because there's a lot of tools for that specific thing, for those specific things. But yeah. Anyway, it was very interesting to do it, so that you know kind of how it works under the hood and everything. All right, so this if here, I'm probably not going to be here for too long, but I just wanted to show the progress a little bit and show a little bit of this IR stuff here, which I think is really cool and interesting. So we have this then, and then we set the result to the then value if we get here. So because otherwise we jumped over this, right? So if we get here, that means the condition was true. We run the then code. We also set the result here, and then also we jump to after here, the label after. Okay, and here's the else start here, and yeah, so here's another weird thing, because the if expression doesn't have to have an else branch, which could affect the whole structure here. So if we don't have an else branch, we might skip some stuff here. We don't really have to have an else address. We don't really have to jump at this point. So yeah, basically the whole thing kind of changes because of that. So but yeah, if we have an else branch, we have two different kinds of else branch. So either we just have an else, which means it's just an expression that we compile, and we should get the result in this else that we can then also set. So we need to set here as well. We need to set the result to else value. There we go. Okay, and then yeah, this would compile this expression, and if we got another if, it means this is an else if, and then we just recursively call this. Why do you want a compile? Okay, yeah, I already answered that question. So I think I read it again. Anyway. Okay, and then we set the label. So basically now we have this result. So what we should do now is just return the result, which is the ref. This would be like from location result. And what this means is basically the kind of the whole result of this entire if is gonna be this result ref, which is kind of like a variable that we set, that we declare up here. If we get into the then clause, we set the results to whatever came out of then. If it's the else clause, we set the result to whatever comes out of the else, and then at the end we return this variable. Basically, that's basically what's happening here. So it's kind of like a function almost, or just a place where you declare a local variable and do these things. So yeah, and yeah, so now I'm not really sure about these refs because it's like a new concept that I thought about, and it might work. I was just thinking like, hey, we should just have these refs that are the only thing they are, basically they're unique representations of some kind of location that you can store things in. So this is a location where you can store things in, and we set the value of the location to this value. And probably this location would be probably tied to the scope or something. I'm not sure. It's just like an anonymous variable that you can return. Okay, so anyway, to be able to talk about the result kind of like this. Okay, so that's the if statement. However, let's say we just create an if now. So first of all, I want to see if this builds. No. So where's the issue here? Oh. Ah, here we go. So we got this consider. Okay, so I basically tried to use a tuple as a key for a hash map using auto array hash map, but it seems like it didn't know what to do with this. So we have to consider using standard hash auto hash strat or providing your own hash function instead. Okay, so let's try that. I believe this is labels. Yeah. So here's that. Now I'm not sure how to actually do that. Maybe you have to do like array hash map. Yeah, and then so the first one is the key type, second is value, and then we have the context, which we need two functions. We need hash and equal. Okay, so let's see if we can use. Okay, and what is store hash? When false, this data structure is biased towards cheap equal functions and avoid storing each key hash in the table. Well, it's a string, so it's a string combined with an integer. Okay, well, let's just see what they mean here. So we got this auto hash strat, which Wait, what does this actually do? We get a void out. Provides generic for any eligible type. Strategy provided to determine if policy should be followed or not. I don't understand. Why do we not get anything back from this function? Like, what does it do? Is it supposed to be on the type itself? Wait, yeah, okay. So then we would have this hash function. Store hash. Oops. I think I'm just gonna say true there. We could check how they do it with string array hash map. Array hash map string context true, right? It's storing the thing. So let's just do that. Okay. Is that the same? No. Wait, hash? Auto hash. No, that is the same. Okay. Oh, this is the hash function. Okay. So, right. So this is the hash function we need to supply. Self and key. Okay. And then equal. So actually we need like self is, what is self actually? Is that the hash table? Okay, context. Oh, okay. So the context is like this. And then key is this. this would be U32, I guess. Or yeah, that's what it was there. Okay. Okay, so that's what we want to have. Now I'm not sure what this is doing actually. Like, what is auto hash strat doing? It's a strat. Provides generic hash for any eligible type. Strategy is provided to. Like, I don't understand how to use this. So you get a key, right? A hasher, yeah. We get the strat, has unique representation. We call hasher update. But that requires an update function. And then we switch on this. And we should have like a struct. We reuse hash of the previous field, see for the next one. Okay. So this would work because it's just a tuple, which is just a struct. So there we go. But how would we use this? I don't really understand. We're switching on that. This just calls hash. So it calls itself, okay. But then what? Where's the result? Is it supposed to like update something? Like it's supposed to... Yeah, okay, so here we're calling update function. So we need an update function if you want to use this. Auto hash. Hasher. So do we need to add a hasher as well, or what? Let's just check this. So string. You have the string context. So you have an actual context. We're just calling hash string. Okay. And then we need the equals. I mean, we just call auto hash, but we don't have a hasher though. This uses this one. I guess we just take this one, I guess. See the 0, okay. I wonder if this needs to be passed in as a variable, and then we need to like extract. No, well, this is a void. Slices as well as union structs containing slices are rejected to put ambiguity. Oh, okay. Maybe that's why it failed. Well, I mean, we only have like 2 things. So basically, let's just create a hasher, maybe. And then we call hash. Okay, what does hash do? U64. So this would create a new one using the seed. Okay, maybe we could use this. But why is it a 64 now? Okay. Let's do... So we don't need to keep the hasher around, I guess. I thought that we would need to do that, but okay. Let's do this. Let's do, well, the key is going to be key.0, which is the U size here. So we're going to auto hash that. Oh, wait. Alright, so it's doing this. Okay. So it's like, yeah, it's doing some hashing there. And I guess this would be updated. Do we get like, okay, so then we can take the final, which I guess would be the result, and return that. But it's a U64, which is weird because it doesn't work. What the hell? It's just truncating it. Does that work? I mean, I guess it would be the same. We're just stripping off the 32 at the end, or at the beginning, however you see it. Okay, fine. So let's do the same thing, I guess. Okay, so we're hashing that, and then we also auto hash 1, except we don't auto hash, we do hash where does this live? So it lives in standard array hash map. you're just putting the string in there, so couldn't we just say this? I mean, it should do the same thing. Although this is looking at like type contains slice. It's an error. Where is this hash function coming from? Auto hash, hash, auto hash. We could just use this one. It should have a unique representation. Let's see, struct. Or maybe it doesn't, I'm not sure. Let's look at slice or pointer. If it's not equals, okay, so it doesn't work with slices. Input, like, could we just put this in here? Is that how it works? Because yeah, this calls update with that. So you should just be calling, like, be able to call update with whatever you want here. Yeah. Okay, and then we just return this. I don't think we need to do the as thing, because it already knows the thing. So that's the hash context. And we don't need that. Okay. And this is an auto array hash map unmanaged. Okay. Now we need an equal function. Wait, auto? No. It's an array hash map. There we go. And we need an equal. So now we need an equal function. I'm gonna double check this here. The equal is self kk usize. What is usize then at the end? Final usize in equal function represents the index of the key that's already inside the map. Okay. So we don't really care about that, I don't think. Alright. So, I mean, we basically just want to check. There is a thing in, I think, meta equals that compares to of any type for equality containers that do not support comparison are only comparable field by field basics. Pointers are not followed. So if we have a struct, if we go through each field, compare the things. Now the question is, what does it do with slices? It checks pointers and oh, so it doesn't check the contents. Okay, but basically it's gonna be pretty simple because it's just gonna be like 0 is equal to. Actually, you know what? This is pretty simple because it's the way these labels work is that each like the first one is actually like it's actually the index of when it was put in, and you can't remove labels, so basically that would be a unique representation of the thing anyway, so we don't actually need the key to have the string in it. Actually, it was just a way to format the thing. Okay, so actually we don't really need the string in here. Okay. And of course this is a bool. There we go. Right, so now the labels should work there. Well, in theory, let's go to the code, test this, see if this still works. I'm gonna go over here, just add a new line here so I get a little bit of separation. Okay. So let's do like if true echo it is true, else go it is false. Okay, so we actually get a whole bunch of stuff in here now. Cool. Now the jump instruction is not really formatted. Will this be open source? Yes, you can go look at it right now if you want. Link is actually in the description. Although you have to keep in mind it's like it started out as an AI experiment basically, so there's a lot of like AI slop in the README and some other places as well. So I'm but I took over and I'm basically replacing almost everything at this point. So yeah. All right, let's check this jump instruction out because I want to format that a little better. Right, we're not even using the format function here, so where is the format function of the instruction? It's here. So if we have like jump, we are going to do this, and then yeah, that's basically, I mean, these could basically be like inline, exit, jump, they are the same. All right. Okay, now we see a little bit more here. So basically this means that we're jumping if the condition is not true. The condition is basically just this literal here. If it was something else, it would point to, it would be like an address or something else. And then this is the label where we jump to. Now labels are not actually shown here. So this label is like, we don't really know where it goes right now. But first we call, like, if true is false, we will jump to the else, which is, I think, over here. It's interesting. Okay, we got unsupported instruction with the jump here. Yeah, so we need to implement the jump instruction, the evaluation of it. I want to be able to see where these are, but okay. Not really sure. I mean, maybe the labels could be in between then, perhaps. We could also, well, the labels could be, they are kind of sorted already. Well, not really, because you can create them without knowing where they end up. So basically what I was thinking, like, we could sort the array, the labels based on where they are in the code. And then during, when we print them, we would be able to what am I saying? We sort them and then we keep a counter to see which instruction we were currently at and check, okay, are we at this address yet? If we are, then we show the label and then we increase the counter. If we're not, then we just wait. So that's kind of my idea there. However, we do need to have the labels stored somewhere. So actually the labels are kind of going into the read-only data part. And we don't really have that right here. So where is the conversion part? Here's like two IR contexts. Now we probably, yeah, we want to add like labels here. So let's add labels. And we can simply move this to over here. Okay, so that's our labels. We'll just add those there. Maybe they could even be, actually, you know what? Maybe these are just a list actually now. A sorted list. we have the key. And then the address is actually, I'm gonna say the address is always gonna be like the absolute, so I'm just gonna say this is a usize. I think, yeah. And I think we'll just remove this, put this back at the other place. And then the labels, these ones would be converted from the other one. And now you are you actually are a label that we can then check. Okay, so yeah, you need labels. So this is gonna be the labels. Let's just extract them here. So this would be labels, map. There's no to own slice here. There's clone. We don't want to clone though. There's no like move. Okay, there's move. Oops. Move, which gets itself. Okay, well that's not what we want. Fetch, remove, maybe. Like everything. Okay, let's just do this. Let's just do, this is going to be equal to allocate labels, and it's going to be labels map count. All right. Then we're going to loop through all of these labels and the entries. So this, well, we actually need, wait, can we loop through this? No, that doesn't work. Actually, we could loop through 3 things at a time, right? So this would be data. Okay, key value. Yeah. I'm just gonna do this for, so we don't have to spell this out. Okay, well, not much of an improvement, but okay. No. Okay, so what we get is we get the label, we get the key, and the value. Okay, so that's what we get. Now these are unknown, but this is known for the LSP. So we populate the label, and we say that the key is key and the address is the value. Now this is probably gonna be an error now because the address is like that thing. If we get to this point and we don't, we have like an unknown label, we probably want to generate some kind of error here. So if the value is null, actually let's do like adder equals value or else return error. That means we have like an unmapped label, so it's like a compiler error. So label adder not set. So now that means we should have an adder there, but it's probably like the wrong type here now. Expected view size, found that. So this should always be like an absolute. I think what I'm gonna do is I'm gonna force the map here to actually be not adder but actually the absolute. All right, so you're gonna be set, you should be absolute as well. And then set label. So yeah, this is gonna be like, you're not gonna be able to set the label to relative. There we go. And now you are also use size. Current adder, I'm just gonna say this is abs. Same thing here. Oh. Okay. There we go. So now we should have the labels also in the context. And then when we run, we show the things here. Now we're kind of moving through the instructions like this. Also, oh yeah, we need to sort them now. So we sort them by address, actually. So let's do like labels. So basically there's like a sort function here, and we sort labels and we sort these ones, and we don't really need a context, so I'm gonna set this to undefined, and then we need a less than function. So label less than. So this is A, B, return a bool. I think it also, they wanted us to have a context here, which is the first one there. So I'm just gonna say whatever, any type. All right. Now, so basically this is just gonna do like address. So basically we just return if A is dot address is less than B dot address. So here we go. So now we're sorting them by, I'm not sure actually if this like ascending or descending. I guess it's like ascending, maybe. Okay, anyway. Well, I guess we'll find out. So, yeah, so now they should be sorted in place as well. And then, you don't need anything else. Unable to resolve comp time error. Oh, you need yeah, that's comp time, labels, context. Maybe the context is what it can't deal with. Yeah. Wait, context? Insertion context. Items, subcontext. Okay. It doesn't know what the subcontext is. I guess this would be the compiler. Oh, where do we provide it? Oh, we provide it. Oh, I see. So we just provide. Okay, let's just provide self then. Alright, there we go. So now that should be sorting there. Okay, so let's go back now to the runner, and while we're printing out the instructions, we also want to keep track of the label counter. So we start at 0, and then we'll check here each thing here. We're gonna check the labels. Well, first we need to check like if this is less than the length. Yeah, that should be enough. Let's just nest it, whatever. And then we have if the label address is equal to I, then we show that. It's just something nice about the simplicity of an instruction having an address that's just a number, and you can just compare. I just like that about assembly. It's like the simplicity is really nice, but also very hard to work with as well. But yeah, so this would now be a label, so we just show the label here. So we're just gonna say S for the name. I'm gonna include perhaps the number as well, because that makes it unique, and that's the label there. And do we show like the address as well? No, we have it already, I think. Yeah, we're showing the thing down here. Should we have like this in an else? We could do something like this. So label P0. And then the instruction after, so that we kind of show, and then we continue there. Alright, so now the labels should be shown. Oh yeah, and then also we add, no, we only do it here. Yeah. Label counter plus equal 1, then continue. So that way, like, we're searching, basically searching for the next label. Alright. Cool. Okay, now let's see if that works. So here's if else label. Okay, so here we can see we got the one if else label. Okay, the thing is reversed here, but yeah, it does show that here's the else label, here's the after label. Okay, cool. Let's, I guess we reverse this. We should also have, we could have it as a, actually this already has a format function, so, but that's not on the label key itself though. So if you have a tuple, can you also have a format function? Tuple declaration cannot contain declaration. Okay. Well, that solved that question, I guess. That's too bad. All right. We could also just not have it as a, I guess we could also just have it like this. Well, actually this is not adder, this is like the counter, and then this is the name. I guess this is, no, yeah, the counter, that's fine. And then we have the format function. Yeah, S main counter. So now we'll do that. Actually, the label itself could have a format function as well. Which is basically just this, where we just format the key. Alright. So now this is just F and label. Okay. Right, so now you are counter. counter, and you are name. There we go. Okay. Cool. Now we see if else over here. This over here. Yeah. Cool. They are labeled. Now we could put them in at different lines if we want as well, but whatever. All right. Cool. So, okay, so here we can see that, okay, we've got, so first we do like, okay, this is if true, this is the jump. So we're jumping over here basically to else if this was false, but it isn't false. So we go through here, we push these things, which is now, here we have more things in the data. You can see the echo is duplicated, which, you know, this is a raw behavior. Now you can implement some kind of optimizer that will kind of, you know, squash these together into one place. It will kind of analyze every, you know, place where you use echo and then squash them into one place so we can reuse that. But it's, you know, optimizing a little bit for, basically for memory is what you would do there. It's not really super important right now. But then you can see all these raw strings here. It is true, it is false, and yeah. So that's what that's what's being pushed over here, and then we push this call there. So let's see here. So we basically, these things work, and then we get the hello out from this first echo here, echo hello. But then we get to the jump and it says unsupported instruction because we haven't implemented that jump instruction yet. But it should be pretty easy to do. We'll go to the compile, no, not the compiler. We'll go to the evaluator. And here we have all these switches here, or cases here for run instruction. So let's do jump. And yeah, so jump has a bunch of different things. So we have like the condition, which could exist or not. It could be an unconditional jump. So if it's unconditional, we just execute the jump. We don't need to check anything. We just jump to the destination. So that could be our first thing here. So we could do like the condition is equal to jump condition, or else we would execute an unconditional jump, which basically would be like self instruction, context, instruction counter, and we'll set it equal to jump and then destination. And now the destination could be different. So we need to be able to resolve an address now. And let's just add this thing here. So resolve address. So there we go. We could also check, we could also do like, we could do a switch. No, but that's what resolve address should do actually. Yeah, let's just add this here, resolve address. We get an address, and I guess we might have some kind of error, we'll see. And then this would become a use size. So we'll switch on the address. And we could have an absolute, which is pretty easy, that we just return let's actually do this. Let's just return the absolute itself. We have relative, which means we should just return self and then context instruction counter plus relative, and hope that it doesn't overflow or underflow. Maybe. I mean, we could do this, but it wouldn't really be accurate. So if it does that, that's a compiler error. That shouldn't happen. Now, I'm not sure if this is actually, this should be doable actually, because this is smaller than this. I'm not sure if we need to convert this here. It would be a pain if we have to do that. And then we have the label. So yeah, this is the label key. So basically, okay, we kind of lost. Okay, I didn't think this through. We did lose the ability to look up by key now by converting this to just a list of labels. So I mean, they are sorted, so we could do a binary search, I guess. But it's probably better to just keep it as a hash map, because then we wouldn't have to re-implement that stuff. We just needed to sort it. Okay, let's just keep the array, the hash map here. So we'll go back to compiler, we'll go to labels, and I think we just move this. Yeah, let's do the thing that we didn't do before. Let's move this over here. Labels. Well, actually, let's just say that this is labels, actually. And then we'll do get. And that's the key. We actually get a use size. Go. There we go. So resolve address. Right, now your label. So here we can say context labels get label, and we are going to unwrap it because the check, they should all be there at this point. Okay, and then now we need to change the compiler. Strange that it doesn't complain over here, but yeah, this could be, let's just make this and then labels. I mean, we could just move it, I guess. We move it. Yeah. Do we need to try this one? No? Okay, cool. But it would be nice, yeah, we want to sort it as well. So if we sort it, is that possible? Can you sort? Yes, you can. But you need a context now. Wait, what do you actually do? Sorts entries and rebuilds the index. Must have this function. Okay, okay, cool. Alright, so the context is like sort. You know what? Let's just add this function here. Sort. Sort, and then this would be, I guess, self. And we need a less than function. Size. So I guess we could use this to get the key. Counter is less than, no, not counter. No, we don't need the key, we need the value. It's less than this. Go. So now we can just sort the labels. And now we lose this check here. We could still go through and check at this point, but we don't do that. We go through the values. Labels .map.value. So we go through every value and yeah, this is what we're doing basically. There we go. We're just checking if value is equal to null. We want to return that. So we're just going through and checking that so that we know that it shouldn't be null there. Okay. Merry Christmas, by the way. Alright, anyway. Okay, and then we just sort the thing. Fine. And then we move it over. Okay, cool. Now, right. So you get the label there. Actually, there should be an error here as well. Yeah. So this should be like map count. Map values. Label counter. Less than is not pub. Okay. Let's go over here. Make this public. nothing more name format. Oh. Wait. Oh, I see. So it's not a label anymore. It's just the apps. It's just the address. Right. Okay, kind of stupid way to do this, but now that should be good. I mean, okay, maybe we should actually convert. No. All right. Right, so there we go. Incompatible size or types. How do we want to do this? Because basically, we want U size to be converted to I size here, because otherwise you wouldn't be able to like. Yeah, if we convert this to U size, it will lose the sign bit. So we need to convert this to an I size, which could potentially, truncate it, but we don't really care about that. So let's just do like I size truncate that, which will make it into an I size result. But I'm just gonna int cast this, and if this somehow gets negative, this is gonna crash here. Expected assigned integer type. What? Okay, wait, truncate. Yeah. Use intcast to convert numbers guaranteed to fit the destination type. I mean, do I have to like int cast as well, or? Or do I only have to do int cast? Let's just do this. It's kind of ridiculous. Yeah, and now we have to, what? Okay, let's just do int cast. Okay. Right, so we need to continue here now then. So you are not an error. There we go. So anyway, back to this. So we have a so this is an unconditional jump when the condition is null. So then we just set the construct or instruction counter to resolve address, and then we should be done with that. So that's that. Now the thing is that we get some kind of result here. After we run the instruction, we always increase the counter. So either we need to like decrease the counter by 1 after the jump, or we have multiple things doing here. I think we just decrease. We just set it to like -1. So that that's good. And then here, now we just return, just continue. There we go. And what we return here is basically either you continue execution or we exit with some exit code. That's basically the idea there. Okay. Then, now if we get over here, we have some kind of condition. So we basically want to check, like, is the condition true? And now we should have a Boolean value. Now it has to be Boolean because that's like it's checked in the semantics. So it's supposed to be Boolean. So it's not going to be anything else. If it is, it's like a compiler error. So we just check the Boolean. So if the Boolean is true and we're jumping if the Boolean is true, then we jump. So if both of those are true, we jump. And this is basically, this is used for kind of negating the condition. So it's like it's putting a not at the start basically, because when we do an if, we want to jump to the else branch if the condition is false. But if its condition is true, we want to keep going into the true branch or into the then branch. So that's how I did there. But anyway, so if both of these are true, we want to do execute the jump. So we will say, well, basically the same thing here. There we go. We could also like do this, resolve jump destination -1. So that's our destination. And let's just do this a little bit easier to see. Okay, but otherwise we don't jump. So we just return continue. And over there we also return continue. So we could also just do that for more simplicity. So if we jump, we set the instruction counter to the destination and we continue. And then same thing here. We could also actually put this in an if here. However, we're kind of using cond. Actually, no, because then we need a nested if. Yeah, I was thinking of, because this kind of looks like an if, like one of the branches, but we can't. There's no way to kind of neatly put these together, and that's one of the gripes I have with this kind of syntax. But it's cool when it works like this, but then it's also like, well, I kind of wish I could incorporate this better here, but whatever. Expected users found that. All right. Oh, right. What the hell? Okay, you know what? Let's just unwrap this. Because we only call get when we're at evaluation, and then everything should be there. We should really have like a different, we should really like change the types, like, but yeah, anyway. Alright, so now I think ifs should actually be implemented. So here's like, we jump to this if not true. And we see the instruction counter didn't change. So we didn't jump. So that is good. Because true is true and true is not false. And so we're doing this and we're saying it is true. And then we should I see. Set is not supported. Okay, cool. So we kinda, yeah, the set, we do want to have like a new ref at this point. Or we have a ref that we use. Okay, this is where it gets a little bit shady now, because I'm trying to use the concept of having refs here. It's basically like a local variable that you can set the location. It's basically trying to say that, hey, I want to talk about a result that I can return, and then I can set to a specific value using set here whenever we have it. So this basically, we're setting result to the value of then. Or if we're in the else branch, we set the result to the value of else. The problem is though, I don't like how this should work in like the actual evaluator is kind of unclear right now, but or what it should compile to as well. We have this set instruction. So let's just see how it goes here. So we have the set instruction. And you have a location, which is the destination, and the value, which is the value. So fair enough. However, the location isn't always straightforward now. So the location can be a ref, which is basically just a view size that is the same as the instruction or the address. You know, it's just a counter that shows which ref we're talking about. So it's basically like a unique identifier for the ref. So also, I think the registers, I'm just gonna remove the registers. I don't think we're really gonna need the registers at the IR level. So that was just a fun thing that I added. I think we're just gonna remove that actually, because it's just gonna be an annoying thing to have with us everywhere. Yeah, let's just remove that. There we go. And then we have the compiler has registers that we just removed. There we go. All right. So with that gone, we have data, which is like the read-only data. So if we're trying to set read-only data, that's going to be some kind of error. Of course, that shouldn't even compile, so that's going to be weird to have here. But I guess that would be some kind of runtime error as well. But we can basically do this. So if we get data, I guess that should be, you know, some kind of error here. Actually, let's just return. And you would be what are all these errors actually? Oh, it's all this. Okay, so this would be like an unsupported set location. Or is really not unsupported though. It's like setting to a read only. Setting immutable, I guess. Set immutable location. Okay. So that's the data, and then we have, whoops, think. Alright, ref and scope. Now scope, I'm not really using right now, so I'm not really sure what to do with that. It's just an identifier into the scope. So basically, what you could do I guess we have context, and then we have the, oh, we don't even have scopes here right now. We should have scopes in the context. The scopes thing is kind of weird. Like, I don't really know what to do with the scopes right now. It's just, it's gonna come into play when you have things like functions and blocks and things like that. Like, how are we gonna implement closures? How we're gonna implement, you know, like current working directory scopes. I mean, I guess technically it could just be, no. I'm not sure. Like that, I have to think about that. But that's basically what the idea of the scopes are. They are, I guess, more high level kind of containers, like that you can push a frame onto the scope. You will create a new scope, and then inside that scope, everything that's executed in that context, and then you pop the scope off the scope stack, and yeah, you will be out of the scope. So that's the idea, which is a construct we do have in the other evaluator right now, which works really well, and it's used for basically all kinds of things, like the environment maps, the current working directory, spawning processes, keeping track of those, yeah, just you know, variable declarations, and all kinds of things. So allocating things. So basically, yeah, we have like allocating scopes. So basically, yeah, that's how it is. And also like allocating things, like having dynamic arrays, or yeah, things like that. We don't really, I haven't really thought about exactly how that should work here. And but yeah, we're probably gonna have some kind of allocation instruction where you can allocate some memory, and using, you know, some kind of, I don't know, page allocator to allocate those things. Probably gonna do something like that. We'll see though. And then also, like, yeah, there should be some kind of garbage collection going on. So there's some cool things that we could add, that's gonna be needed for all the features. Right now I'm just trying to get like the basics in. So I think for now the scope is like, I'm gonna say this is like an unsupported right now, unsupported instruction right now, I'm gonna say. All right. And then we have the ref, which I'm also not sure what to do with. So we have the ref. Now the ref is kind of like a variable location, so it could hold like a value. Now what we could do is probably have it in the context. We could have like the refs here, which we just set based on the, yeah, it would just be based on like the number. So basically we would have refs, and then this would be like, I guess, like an auto array hash map, and it would have this, the key would be usize, and the value, so this would just be a value here, and that's it. So that's the refs. And then back over here we could say like, well, we could try to get the ref here, get the entry maybe, or the pointer of this ref, which should exist. Actually, you know what? We can actually now have a declare ref instruction as well, because that's gonna pair. It's gonna pair with this. I guess maybe if the ref doesn't exist, we could probably just create it actually. Yeah, but if it's not declared, it could be some error. So I think if we should actually add like a declare ref instruction actually. So because we have the set, let's also add like declare, or maybe ref, just new ref, and it doesn't really need anything. Declares a new ref. So that doesn't need anything, I don't think. It's just ref. Okay, so now in the compiler, when we create the new ref, we actually also want to, so this is the ref here, and then we say instructions or add instruction. Right. Return ref. So this would be some kind of error. We add instruction. I was just an allocator. Okay, so we add instruction, and the value, no, the instruction is just gonna be ref. And I guess we could add a source here, which could be, let's just do anytype. So now you need source. Alright, cool. So that's still the location, except now we need to try it as well. Okay, so now this actually produces an instruction now. Right. Okay. So let's actually make this here as well. So now we have this one. So we just want to say that we want to put the, oh shit, we actually do need something here. I mean, technically we really don't, but we probably do. I'm just gonna say that this is gonna be, yeah, because if we already, like whenever you call ref, no, it's gonna be, I don't know, maybe this wasn't what I thought it was from the start. Whatever, let's just do this. So this would be like ref dot ref, and that's a new size. Okay, I don't know if this is good pattern or not. We'll figure it out. And I do want to change this if it's bad and replace it with something else, but I'm just gonna do it until it doesn't work, and then we'll figure it out. So that's the use size, that's the ref. The value's actually like void right now. When you declare a value, it doesn't have a value, so I'm just gonna say void. Alright, and then here we actually get the pointer, right? So this is the ref pointer, and if it doesn't exist, that's going to be some kind of error. So this is going to be like ref not found error. All right. And then we can say that we want to populate this with the value that we get from set. There we go. And all the values are basically going to be, you know, they're not going to be allocated or anything, so we don't need to like worry about memory management there. Okay, I guess this would be kind of like an allocation error, so let's do that, and then we'll return continue. Cool. We could also check if we had this error like this ref before. That could be an issue, like ref, like a double declare on the ref. So I'm gonna do get or put and it's gonna be the entry, and then we're gonna check if we found an existing. We're gonna return duplicate ref error. Alright, otherwise we are going to set the value pointer to be void. I guess, I mean, yeah, okay, we'll set it to void. We don't really need to set it here actually, because it's gonna be like undefined, and then we're, you know, well, I guess it's better to set it here to not get some weird errors later on. It's just if we're using it correctly, then we don't really need to worry about setting it here, but we want to be on the safe side. Okay, cannot dereference non-pointer type. Alright, let's do a try there. No, wait. This is not a try. What's happening here? Cannot dereference non-pointer. 1 second. Alright, I'm back. Okay, so we got some issues here. One thing that I would want to do is also print the refs and the set now to show what they are doing. Also, this jump doesn't really make sense. This should be a non-conditional jump, so it should always jump. and but it doesn't. So it's showing like it's a conditional jump which jumps on true and false. So yeah, let's go to the compiler, and we can see this second jump uses condition which is wrong, so this should be null, which is the unconditional thing there. Wait, this says like result. Hang on. Oh, I see. Let's do that, and then if condition we use value, else no. Right? Okay. So expected bool found there. Oh yeah, sorry. So that's the comp there. There we go. Okay. And then let's see. Is that it? Alright, cool. So let's check this now. Yeah, so now this just says true there. So it's like unconditional. And here you can see the instruction counter also jumped, and we don't see the other echo now. We just see it is true. So it jumped over the thing, and now we're at the end, so we exit. So there we go. Cool. Let's do the ref thing. It would be cool if we could get the ref like result, but we don't really. I guess we could try to do that, but we don't. The thing is, we don't have the scope. So how we would do that is basically, if true, we would do like 1, otherwise 0 maybe, and then we bind that to some thing, and then we would like try to examine it or echo it out. Now also one thing is that we don't have string interpolation in IR, and we also don't have, you know, looking up things in the scope right now as well. But I just wanted to see if this would actually be, you know, the thing. So let's actually do, let's try and do well, we can't do this, so I'll do if true, and then we can have another if, I guess. Wait, how would this? No. Yeah, so what you would do is like this: if true, then true, else false. So this would use whatever result we get from this expression as the condition. So that's what I want to check, if that is possible now. Okay, it is true, else echo it is false. Okay, so what would this be? Well, we got some weird error now. Okay, cool. Okay, interesting. So basically, yeah, we actually now got a location instead of a boolean, which makes sense, because this is not like yeah, these are like com time known, but this expression is not like, we're not like evaluating it in com time. So it makes sense it's a location. Well, I'm not sure if it makes sense if it's a location. It's basically, yeah, it's a ref actually. So when we get a location, we need to like evaluate the location or look at the location basically to see if we should jump or not. So actually let's do that. So let's, when we do the jump, and when we look at the condition, we need to, so here, so we actually need to like, we need to like evaluate the location or the value, I guess. Resolve the value maybe. So we need to like resolve value. And now it should not be a location anymore. It should be a boolean. So now we do that. And let's add like resolve value. And we get a value in. And we get a value out. But we are going to do value. Now if it's a location, we have these different things. So we're gonna switch on location. And if we have a data, if it's just a data, this just means it points to like one, it points to like an address in the data. And it's not as, yeah. I guess the type would depend on what you want the data to represent in that case. So maybe we actually need like a type which this is gonna be resolved into as well. Because it could be a read only representation. Maybe I'm not sure. I'm just gonna this is just gonna be like unsupported thing here right now. No, unsupported resolve value type. Alright, scope is also gonna be unsupported right now. And then the last thing is the ref. Now the ref, we can just say context refs get like this. Alright, so that was location. If we get anything else, I think everything else is basically going to be whatever it is. So I'm just gonna say that, okay, well then we can just return the value itself. So we can, it's kind of like a dereference here, almost. Right, so now you should be a value. Well, we'll do this first. Let's do a try. And there we go. So now we can actually assume that it should be a boolean, right? Because the thing before was that, okay, well, it only worked for like literal booleans. Now it works for actual, like if you have an identifier which is a boolean or something else that points to a boolean. That should work now. Okay. So, okay, cool. So we got some refs here. Actually, let's improve the ref output a little bit so we see what it is. So the refs, we need a formatter for those. So let's go to here, and I'm gonna say the ref, and I will print well, it's just gonna be ref and then the number, and the number is R. So that's ref. Okay, now we need the instruction. Wait, location. Why don't we see this? Oh, it's because of the format. Okay, so ref is already formatting. Okay. Where's the instruction at? Here. So I guess we'll do the same here. Ref. Let's try set as well. But then we need to actually add a format here. So you would be set location equals value. Oh. Okay, it's slightly different. So this one is not F there. There we go. Okay, so here we see it now. Ref 0, ref 1, set ref 1 equals true. I guess we could copy this style here. It's kind of a weird, like, it's just to see that, hey, it's a ref. Double at means it's a ref. So we should actually have them the same format there. So let's do like at. There we go. Alright, so this is at 0, this is ref 0, ref 1. We set 1 equals true here. And that's everything that's happening there. We're basically just setting the result to true. So, okay. I think what's happening, yeah, we are, this is the condition being executed, because this is like in here, so we're executing the, or we're compiling the execute the condition first. So that's what we're seeing here. This is the condition happening over here. I think all of this is the condition part, and then comes the next, like, well, it's part of this. So this if starts over here at 4, because it declares the ref 0 here. This declares ref 1, and yeah, it just sets this to true. It sets this to false if true is false, which is not, and then we have this after 0 thing here. And then we jump, if ref 1 is false, we jump to if else 3. Okay, and then in the execution, it's just to see that when we compile this in something else and then, you know, using that as a return value, it should actually work to kind of grab out the value inside and use it outside. So that's just what I'm trying to achieve here, and it seems to work if we examine everything here. So I'm just gonna go through the code again here. So yeah, there's the condition part, and then we have jump ref1 if else 3. Now we call the echo it is true here, and we set the result to void because there was nothing like this resulted in void, so we just set it to void. It shouldn't be void, by the way, but right now it is. And then we just unconditionally jump to after 2, which is over here, and exit. Okay, and then we have like if else 3. Yeah, it all seems to work pretty well here, which calls the other one. And then we could see, like, yeah, it's just doing the thing. And this was true, so it never went to if else 3. We call the thing it is true, and then we jump, we set to void, yes, we jump to after 2, which is the end, and then we exit. Okay, cool. So it's like the execution is super straightforward, really. They like the interpreter or the evaluator of the IR of the intermediate representation is very straightforward, but the compiler and the context, like all the design and everything on the language, that's where the complexity lies. Like the execution is basically a CPU reading off instructions, doing whatever the instructions. The instructions themselves are very straightforward and simple. And yeah, just I mean, just like comparing this to the actual, like the evaluator we have right now, it's insane. Although the evaluator we have right now is like, of course, it's way more advanced right now. But I'm gonna try to work with this in the meantime, and try to add more things to it. Like these are just the basic things to be able to have some building blocks in order to like build more things here. But basically now that we have jump and the refs and stuff, we can do things like the for loops as well pretty easily now. And yeah, I'm just gonna add things step by step and see how far we'll get. And yeah, so that's gonna be pretty cool with this IR here. Now, yeah, and then once we have, you know, a more basic functionality, I'm gonna start trying to think about, okay, well, how are we gonna do with the pipes? Like we can actually, like if we look at the command, how that works now. This is the call. This is where we call basically, well, you could call like functions and stuff, but this is only used for executables right now. So basically how it works right now is that we just gather the arguments into the list here, and then we call, you know, child init with argv and the allocator, and we spawn and we wait, and that's it. like in the other evaluator we have way more stuff happening, so this is gonna have to get fleshed out, and I'm gonna have to try and figure out, okay, how would the runtime look for this, and how can we implement these things that we have in the other ones right here and make it streaming and stuff. So yeah, what I'm thinking is like, yeah, we should have some kind of pipe construct, some kind of virtual pipe thing that we can spawn a virtual thread for, that will loop through and forward the streaming. So basically what we have right now, except it's gonna be, you know, a little bit different. So anyway, that's gonna be it for this time. I have to quit here now, but yeah, pretty cool stuff. I really like this intermediate representation. It feels like we are going on the correct track now with the compiler and the evaluator of the IR actually for this language here. The other path was really, it was really like a dead end. It felt like almost. But yeah, we've learned a lot of things. We've learned how to kind of structure the pipelines and how to enable like streaming and stuff for them, and next is like being able to have like more of like background processes and more support for streaming with blocks and functions and all that. So it's gonna be a lot of goodies there. But yeah, this is gonna be it for this time. So thank you very much for joining me here, and I will see you later. So Merry Christmas and whatever, and have a nice day, and yeah, see you later. Bye bye.